In this chapter, we're going to introduce the topic of thermochemistry. And if we were to define thermochemistry, we could say that it is the branch of chemistry that studies heat and energy changes during both chemical reactions and physical changes. So things like phase change, for example. Um, and the main topic that we're going to discuss here is just the nature of energy. So we'll define some more terms here. Some of these you might have seen in other classes, such as physics or biology classes. Energy we define as simply the ability or capacity to do work. And then we should also define work here as when energy is used to cause an object with mass to move. So now that we've established those definitions, let's look at a specific type of energy here. This term heat is the energy used to cause the temperature of an object to rise. So this is what we think of when something's hot or cold. If heat is being produced or absorbed during a reaction, we'll reference this specific type of energy. Then we have down here, you might have seen kinetic energy, maybe in one of your physics classes using this formula here. This is energy that an object possesses by its motion. So in this equation, kinetic energy is 1/2 mv squared here. We can see this bicyclist over here going down the hill has increasing kinetic energy, higher kinetic energy due to motion than when she's in this position here. So she has high potential energy, but no kinetic energy. And lastly here, to define potential energy, we can say an object possesses this type of energy by virtue of position or chemical composition. So here we see the bicyclist, her position gives her high potential energy, but also maybe in your bio course, if you've talked about ATP, ADP, and those processes, you would know that there's potential energy stored in certain chemical compositions. So this next image here, this shows some other types of energy, specifically sometimes called the lattice energy, which is this electrostatic potential between positive and negatively charged things. So this force of attraction that's seen in ionic compounds is sometimes calculated as this electrostatic potential, this E sub EL. You won't have to do this calculation, but it's good to know that there is a measure of an ionic compound's energy of it being held together. And what we see over here is that when we have certain compounds, certain charged particles, a certain space or separation distance is the perfect space so that um, we have this energy so that the ions will combine. Any energy other than that, we can see like charges would repel, opposite charges would attract, but this greater separation gives us less attraction. So that's kind of what this image is showing us over here, that we need a certain distance of separation. That's alluded to down here, this D, and then we can have these opposing charged particles being held together. What is more important though is this unit mentioned here, the SI unit of energy, which is called the joule, which is abbreviated with this capital J here. We should also note that sometimes in calculation, we might need to use this equivalent value for the joule, which 1 joule is equal to 1 kilogram meter squared in the numerator, and then in the denominator, second squared. So at times we may need to use that as a conversion factor here. We also may see, maybe not in problems on an exam, but there's an older unit of energy called the calorie, such that 1 calorie is equal to 4.184 joules. And the calories that you may think of in food, this right here, one capital C cal is actually equal to 1,000 of these other calories referenced here with a lowercase c. And sometimes we say that 1 kilocalorie, this 1,000 calories, is the equivalent. So you may see this occasionally brought up in some problems where we convert from the calorie to the joule and vice versa. The last topic we'll discuss here is what's referred to as the system and the surroundings. So the system that we're referencing here, these are the molecules that we want to study. And then the surroundings are simply everything else in the known universe. So such that when we add the system and the surroundings together, we equal the universe. So when we talk about this specific example shown over here, the molecules in this combustion reaction here within our system, we have maybe H2 and O2 gas molecules in this piston here. And those are going to be our system, and then the piston itself, the cylinder, everything else is going to be our surroundings. And again, the system is just those gas molecules inside here. Now, when we talk about energy, we should note that energy, we'll see in the first law of thermodynamics, cannot be created or destroyed. But we can transfer energy from one form to another. We can also transfer energy in the form of heat. And energy can also be used, we can note here, to move an object over some distance. And this is given by this equation here. So this is our equation that relates work. So W for work, some force, so some energy being utilized to move some object over a distance. I noted a second ago, energy can also be transferred as heat. So heat will flow from warmer objects to cooler objects. So we have warm to cool. And that's as these warmer objects have higher kinetic energy that's transferred to lower kinetic energy regions. And then last here, we can mention how energy can be converted from one type to another. So maybe kinetic energy can be converted to potential energy and vice versa. There's also other forms of energy that we might encounter, such as electrical energy. And then, of course, food we know has that chemical energy or ATP. The last definitions we'll say here are open system, closed system, and isolated system. So again, our system is the molecules specifically that we're interested in studying. So in an open system, both matter and energy can be exchanged from the system to the surroundings or from the surroundings to the system, depending on the case. So we say with the surroundings here. And we can think of a pot of boiling water without a lid, so an uncovered pot of boiling water. We could feel the heat escape if we put our hand over this pot of water, but we can also see steam rising, so both matter and energy are escaping or exchanging with the surroundings. In a closed system, the second case here, only energy can exchange with the surroundings. So if we have a covered pot of boiling water, the matter is not escaping, so the water vapor is not getting out, but the heat we can still feel if we had our hand hovering above the pot. Lastly, if we had an isolated system, neither matter nor energy are going to be exchanged with the surroundings. And we can remember an insulated thermos is a good example of this. So we'll continue in the next video with our next topics on thermochemistry.